All right, so this is week 3 assignment, and my group is with Baron Curtin and Heather Geiger. And so the first step here is just to load the libraries. We have a few different libraries, but the main one we're going to use today is just simply NetworkX. And then we're going to be using the Facebook data from the Stanford Large Network Dataset Collection. And the main files we're going to be using from this have suffixes, edges, and circles, and then they'll be called, for example, say 0 dot edges, 0 dot circles, or say 100 dot edges and 100 dot circles. And whatever that file name is, if it's say 0 dot edges and 0 dot circles, then that'll be focused on a node named 0 as the main node. And then we're going to create an empty graph, and then we're going to run through these files. And for the edges files, there's 2 columns, and we're going to go through line by line and create an edge between the node listed in column 1 and the node listed in column 2. And then also we're going to connect the node listed in column 1 to the main node, such as 0 if it's the 0.edges file. And then the node listed in column 2, we're also going to connect to that main node. And then the circles files, they have a row number at the beginning, and then after that they can have anywhere from 1 to 100 plus additional fields. And just for each line, for each of those fields, we're going to connect each of them to the main node. And so then we can run through that for all the edges and circles files. And then now Baron's going to talk about graph creation.
All right, cool. So taking the empty graph, we can use the functions add edges from. So in the previous function where we ran through the files, we created 2 lists for edges and circles, and specifically we're focusing on node 0. Afterwards, we use some coloring and some sizing. So for the colors, we use the number 20,000, and it's just to differentiate the colors better, so that we have very distinct colors for very distinct nodes. Same kind of logic applies for the size, where we use 10,000. And these are based on the size is based on betweenness centrality, whereas the color is based on degree. So NetworkX function draw NetworkX just takes all of those arguments and creates the graph. So in the graph, you can see that the main node 0 is yellow, and it's a lot bigger than all the other smaller blue nodes. That indicates that it is the center of the graph, and all of the other nodes are connected to that main primary node. However, you can notice distinct clusters in the graph of the certain blue nodes. So there's at the bottom left, there's one really large cluster. These are just the different circles or like mini networks that are also connected to node 0. So performing the analysis, we can use the NetworkX function .info to get basic information about the graph. We get the total number of nodes, total number of edges, and the average degree. For 2 metrics, we decided to use betweenness centrality and eigenvector centrality. Very easy to calculate using the nx.betweenness centrality and nx eigenvalue centrality, where you just pass in the actual graph and those are calculated for you. Passing those 2 lists into a data frame and printing the data frame while sorting on betweenness centrality descending. We can see that node 0, which is also the main node, also has the highest betweenness centrality. It also has the highest eigenvector centrality too, which is appropriate because it is the main node. After that, we go into the longest, shortest path.
So the longest, shortest path here is we're comparing any 2 nodes. And here we just do it in a simple for loop. So we're looking at the permutations. So some combinations of nodes might be repeated. but just basically for any two nodes, we're going to get the shortest path between them for all of them. So for example, if you're going from node 236 to node 285, there's no direct connection. You have to stop at 0 first. So that has a shortest path length of 2. In other types of networks, there can be even more complex paths than that. But in this case, we're just going to run through all the combinations and get the shortest path. And then out of all your shortest paths for all your combinations of nodes, the longest one of all those shortest paths is also known as the diameter of the graph. And if we look through the shortest path lengths for all those possible permutations, we see that the longest is 2, so the diameter of our graph is 2 here. And for any given permutation of nodes, most of them have a path length of 2, where they're not directly connected, which makes sense when you look at that original graph. Then you see some few permutations that are directly connected. And then when you have a path length of 0, that's just the node's path to itself. So that makes sense. There's 343 of those, which is the same as the number of nodes.